Yeah, yeah, that's a thing. I won't go down the rabbit hole of complaining about the original Monopoly game. We don't need that. Because it's a horrible game that never ends. No, it's decent. Just people don't often play by the actual rules. Like if somebody doesn't buy a property, it's supposed to go to auction. Yeah, like all these different things that are supposed to happen. All right, so yesterday we were missing Jake, and here's the fun of it. And who knows if Connor's going to watch this video or not. But Connor and Akshaya made some progress yesterday in trying to derive a way that we could calculate the area of any regular polygon only being given one piece of information. Either its edge length, its radius, its altitude. Okay, I guess I also have to say we'll know how many sides it has, right? So we will know what sort of polygon it is. So the hexagon was, I don't want to use the E word, but it was nice because, would you like to take over? Wow, shut down immediately. Jake, in a hexagon, what are all of our central angles? 60 degrees, which means, which means if we break our hexagon up into triangles, what we've created is equilateral triangles. And those are nice, right? I don't really like words like easy or simple, but they're nice. So, I mean, you're right. I just try to avoid those words to can make some kids feel bad. So then we said, well, like, what if we had 100 gone? Right? Or like, a nonagon. So we started messing with this nonagon, and this is kind of where we got, where we ran out of time. But so what we did here, actually, I can't remember what we did.
I don't remember either.
Well, I guess we're going to have to do it again then.
Oh, yay.
So, go ahead, and I don't know if there's a nonagon on your shapes template. I don't know how high it goes. Is there a nonagon on there? Grab a piece of graph paper. Sorry, we actually have to write today. Maybe that's why Connor isn't here.
Yeah.
Maybe they knew that we were actually going to write today. There's a 7 gone.
Yeah, there's not a gun.
Which number is it? 23? Yeah, so go ahead and trace 23 on your paper. And give it a radius of 11, right? It's a radius because it goes out to that vertex. So I'll give you guys a second to get set up and going. I might actually do this on paper as well because it's kind of hard to do up on the board. And I guess I can use the straight line tool. So what's the first thing that we can figure out about our nonagon? Almost sounds like it's saying like not a gon. Nonagon. Who what?
Well, the diameter is 22.
Okay. Awesome. Diameter is 22. I love the shapes templates. They let us so easily cheat. So a nice way to make sure that you find the center of your nonagon is crap. This is a nonagon, which means I can't draw from apex to apex or from vertex to vertex and go through the center.
You have to draw from vertex to side.
Yeah, we have to kind of draw from like vertex down to... So I tried to center my base. Well, I don't even know if we care about ruler as much as we care about just like straight edge. So 1, 2, 3, 4, 5 and a half. So 1, 2, and 3/4 is probably, or I can just do another across here from vertex. So essentially if we make a couple altitudes, I think is what we're doing. I make a few altitudes. The best I can, at least. Are you insulting my altitude?
I'm saying my altitude don't look like that.
Yeah, it's a little tough with the odd numbered shape, right? So what did we say yesterday that we really care about from the nonagon that we can kind of like pull out of here and just really focus on?
The one triangle that we made is then more.
The one what triangle? The isosceles triangle. So what we're really doing here is we're going to pull out this isosceles triangle. Now hold up. 18 triangles. I don't know that you need to draw all of those. I mean, we can, right? But I already goofed up my drawing up here. I can tell this is not perfect.
7 is isosceles, right?
Yeah, 7 is isosceles. You can tell by the darker kind of length marks on it. Boom and boom. So, what's this central angle that would have been from up here? Sorry, I was being entertained by Jake talking about messing up his triangle even with the template. So 40 degrees, which since it's isosceles, we said we can go ahead and derive the rest of the angle that needs to happen is 140 degrees. So divide that by 2 and we get 70.
Yeah.
So really, if we drop down this altitude, we also know a 20 in the right triangle. Because Jake just said trigonometry time, I'm thinking we need a right triangle.
No, I just made a perfect triangle and then made an altitude.
What are you yelling no about?
My altitude doesn't look like an altitude because it looks fancy.
Does it matter?
In height.
So what do you mean trigonometry time?
Sine of angles.
Okay, sine. What's sine going to do for us?
Find the base of the triangle.
So if we do sine, are you doing
Tangent. It's going to be tangent.
tangent? I'm just going to leave my sine written there.
Tangent
Of which angle?
70
Sure.
is 11 over x.
No, wait, what is tangent function?
Opposite over adjacent.
Do we know the opposite?
Yeah.
That's x.
It's
No.
11.
No. No, the opposite is x. And then the no. What? No.
It's 11.
What?
You got to say more words, Akshay. You can't just say no.
Wait, what did you say?
Oh, you're right.
I
You're
know.
dumb.
Because they didn't say the altitude was 11. They said,
True.
I know. They said the side was the
Sorry.
11.
So wait, what is 11 if we're talking trig?
The hypotenuse.
The hypotenuse. So I actually can't use tangent here
Yeah.
yet.
I know.
The tangent looks so nice.
So,
Mistakes
yeah,
are how we get to the right answer.
It would be sine of 70 equals x over 11. So it's 11.
Okay, sine of 70, hold on, equals opposite over hypotenuse. So x over 11. So if we're making this, we'll say is x. I'm going to keep a good labeling.
X equals 11 times sine of 70 degrees.
That's what I just said.
And I'm just going to leave it at that because I don't want to do an approximation.
Oh, yeah, you do. Get a calculator.
Oh,
Well, if it's approximate, it's not as accurate.
Yeah, but if we actually need to calculate the area, you can't really give your area involving sine or cosine. We kind of got to take it to a decimal value. So make sure you're in degrees first off. You always want to check that, because sometimes you won't be able to tell that it's making a mistake. 10.34.
Yeah, I got that.
Okay. And then is that all we need to solve?
No.
Well, if we're trying to find area, you tell me.
No, it's not.
Okay. What else do we need to do then?
You need to solve for y.
Why is that? All right, so you can either make y the whole length down here or half of the length down here. I'm just gonna go, yeah, because the trig would involve just the leg of the right triangle. Might as well make y the half.
You can do 10.34 divided by 2 because if, wait, because if it's a 3069.
Is it?
No, it's not.
This is like a 2070 or a 4070 70. I don't think there's any special relationships.
Y equals x over 10 to the 70 degrees.
Or 11 squared minus 10.
So, here's something I will caution you with. We found the 10.34. There is this kind of like unwritten rule in mathematics. Jake, you with me? Because I have a feeling you went down the path I'm about to caution you not to go down. If there's a number that we have derived, and there's a way to avoid using that number to derive another value, we should avoid using this number because we found it and it's probably been rounded. So when we go to find y, we should actually utilize cosine function. So if we use cosine of 70, now we could have still used sine, but we'd have to switch it to sine of 20. So either you could still use sine and use sine of 20, or you could use cosine of 70 equals adjacent over hypotenuse. So now 11 cosine 70.
I got 3.76.
Yeah, 3.76.
It was the exact same thing to like.
I know.
9 decimal places.
I know. But I'm just trying to like instill to you these other rules. If you have a derived number, you want to avoid it if possible. It's not like a hard, fast rule, and it's not even really one that you'll find written down in a lot of places, but it's this like rule for accuracy, right? Why would we use a rounded value when we can use a nice clean value? Hand? Question? Akshay?
Couldn't we have done 11 squared minus the answer squared and then square root of the answer and then still couldn't have gotten the same answer?
Yeah, but we would have still been using this answer, right?
No, but you could use that answer. So
Yeah, but so let's say we type something in our calculator and that answer in our calculator is not actually right. This is another way to check, like, because normally it'll flag something in your brain that is like, wait a minute, these two numbers don't make sense with each other. Like, this is smaller and should be because Hinge theorem tells us that the side across from the 20 degrees is going to be smaller than the side across from the 70. This works out to kind of agree, right? That, okay, this is how it should be. Hopefully I haven't made a mistake. If y came out to be bigger, right, we should have some sort of alarm in our head that's like, wait a minute. So here's the convenient thing. The area of a triangle is half the base times the height. We already have half the base. If we want to look at this entire isosceles triangle,
It's just x, y.
we already have half the base, right? So all we need to do is this x, which is our height for the triangle, and this y, which is half of our base for the triangle. Go ahead and multiply those together. $38.888 or probably 38.9.
38.89.
What are we going to multiply that by?
What?
9.
Oh, yeah.
Oh, yeah. Because there are 9 of these identical triangles. So just about 350. I think probably the only reason that we're off is maybe a potential tiny rounding error. Does what we did make sense? Try it without me on this, which at least this is an even amount of sides. So first you want to figure out what kind of gon is this.
Well, that would be
Yeah, remember octagons have flat sides on left, right, top, bottom. So if it's not a flat side over here, you know it's not an octagon. Decagon, right? Yeah, we say deca, not desa, just really because deci means break into tenths, and deca means multiply by tens. Yeah, that exactly, because it breaks by tens. So decagon, I think, is 14 on your template.
yeah, that would be correct.
There has to be a cleaner way, right? Like, there's gotta be. These are regular polygons. So what we're trying to figure out is what's the better way to do these? And oftentimes the only way to derive the better way, or like the theorem that we're going to try to make into a theorem, really, so our conjecture that we're going to try to make into a theorem, normally it's just through some repetitive practice that we can figure this out. What are we given? Radius or altitude? Altitude, right? What would the central angle be? I love how I said without me. I'm going to shut up now. I mean, here's how I started my drawing. I did an isosceles triangle, but then I drew a right triangle because I think it's almost easier to deal with. If I just separate out the right triangle, man, how are we going to clean this up? Sorry guys, I also kind of have a headache today, so I'm a little bit less like... You guys can come to the board if you would like, but I know I'm asking you to write this on graph paper today so you actually have a reference to refer back to.
Did you try the bottom one?
Oh, you already got it? What'd you use? Okay, well, how'd you find like your unknown lengths? I mean, the 5 is going to be beneficial. I don't think we need the hypotenuse. So, tangent?
That's what I did.
Tangent. 18 would probably be better, so our unknown can be on top. I'm going to go ahead and call this y again, just because we did it last time. Y over 5.
So this is my theorem I came up with.
So hold on, you're jumping ahead of me, because I don't even have this one solved out yet. So y would be, what'd you get for y down here?
Okay, well, I haven't actually used the theorem. But
Oh, well. So you haven't even tested it. You're trying to show it off, and you haven't even tested it yet.
I think it works.
It's like saying, look, I built this car, drive it.
Why you
Don't worry, nothing can go wrong. Absolutely nothing can go wrong. Sorry, what'd you get for y, Akshay?
I think 1.62.
It would make sense that it's smaller than the 5, right? So 1.62 relatively makes sense.
So then you multiply 1.62 by 5. Or, no, that's what you do. And then you get 8.12. Yeah.
So when we multiply this times 5, we have to remember we're actually getting the area of the isosceles,
Right.
right? Not just the right triangle. So this will get us the whole isosceles area. So
8.12.
eight-
You have to multiply that by 10.
8.12, you said?
Yeah.
So then probably 81.2, I'm guessing. Units squared. All right, Jake, before we're going to let you show it off, we got to test it again. So first off, did whatever you wrote out get you to 81.2? That's going to be the first question. So then, Akshay, if you want the next challenge, yeah. Look, it's a hexagon again, though. You pull it back and make it easier.
I love how my notes are, I don't know why.
Right? This is why I make you guys write stuff down, because then it's like satisfying.
That's because of the whatever.
All right, so hexagon is number 5, ironically. I'm going to center it on a line.
And a lot of people don't like proofs.
Math 1 is learning proofs.
Yep.
You should write a proof for them of why they should like proofs. Is the phrase "let's not and say we did" still around?
I don't know.
So our hexagon tells us that we have edge lengths of 4. So we can break that up and say we've got 2.
And then the size of 4 because 360
So
divided by
4 and 4. 4, 4, yeah. So we got 4s everywhere. And then, go ahead. Scale does not matter because, you know, we're trying to use what we got. So we got a 30, 60, 90, with this being 4, this being 2. Ha, right.
So then it would be 2 square root 3 because 3069 says that the other side has to be a times root 3. So yeah,
Yeah, the other way to say it is half the hypotenuse times 3, which works out.
Okay. And then you do 2 square root of 3 times 2.
What's 2 times 2 radical 3? It's just 4 radical 3, right?
Yeah, it's great. So then that's 6.93, and then that times 6, right? Yeah. So then,
Got 6 triangles. This was each of the triangles. I think it's 24 radical 3.
oh, you're doing roots? I'm not.
I mean, radical form is okay. This is where I will agree with Jake about accuracy is nice. So you can leave it in radical form if you want, or we can put it in decimal form. So what'd you get? Should be like 7.
What?
What? No, you're right. This is 1 point something, I guess. 1.5, 1.6, something like that.
1.78.
What'd you get? What?
I don't think I did this.
24 times radical 3?
Wait a second.
I think I get like 41.6.
Okay. And then, because 4 radical 3 is 9.62. And then you multiply that by 6. Oh, I know what it is. Okay. Times 6. 41.57.
You know, if you do more, it might come to you.
Oh, this is the only way? Oh, I like it.
This
Makes
is
me
the
feel
way.
smart.
This is the way.
And it's fun to use this geometry.
There is not a shortcut here. At least not one that I'm going to give you.
Oh, okay.
So here's the issue. There's too many moving pieces. How many sides are there determines that central angle. Whether you have the edge, the radius, or the altitude changes what trig we use. Right, so Jake, you're over there about to have your brain explode when there might not be a method that works for all of these. We might have to start to kind of like section out the different types of problems we've been given. Like, we might need to say, there are 3 ways to shortcut this. 1 if you have the edge length, 1 if you have the altitude, 1 if you have the radius. And at that rate, couldn't we just like do this every time?
I mean, I find this fun. So.
Yeah, like this isn't bad, right? This isn't like no one's like pulling your teeth or giving you a root canal. This is just break up the shape, do the trig, and put it all back together. So Jake, what I'm trying to make sure you guys hear is there is not one magic bullet for areas of regular polygons. However, this technique is like the shortcut, right? Of break it into isosceles triangles, break your isosceles into right triangles, and work it from there. Obviously, hexagons are going to be the nicest because they make equilateral triangles. But like, what if we had a pentagon? So like, let's try this again, but real life situation. If we have a pentagonal area that we need to fertilize, fertilizer is expensive. You really don't want to overbuy on stuff like this because then it sits in your garage and it normally goes bad. Because if it gets wet, if it gets exposed to moisture, it's done. So we have 15 feet on the edge. Now, if you think you've derived a nice process, sure, go ahead and try to use that. Otherwise, let's just use the process that we've been doing of break things apart. Gotta love breaking things. Now, I'm not telling you quit searching for a better way, because there are always math prizes out there available to people that figure out something that other people haven't.
Like mine.
Yeah, literally, money. It's got to be higher up than that.
Oh, this is a decimal credit.
Oh no. Oh no. So really, I don't really have to think about the isosceles triangle. I can jump right to the right triangle as long as I remember how we're subdividing. Here's what I mean. This peak angle. Yeah, we have to divide by 10 to get there. So you take the n. So wait, so if we want to start to derive how to get to the trig part, this was 360 divided by, here it was 10. Ooh, not 5. If I'm looking at the right triangle,
Oh, okay.
it was 360 divided by 2n, right? So for an n-gon, Jake, you with me? Because we're cleaning some stuff up now. So 360 divided by 2n gives us the right triangle's angle. One of the right triangle's angle, which here is 36. Then we can figure out the other angle as just the complement, right? So here that would be 54. This we said is 7.5. Not a very pretty center here. And then what do we do? What if we just try to make a rule for when we have the edge length? Would that help if we try to make a rule for just when we have the edge length? So with edge length, and we know the 36, what function am I going to use then to figure out the height here? Tangent. So, dude, do more. The only way to figure out what's happening is do more, right? Like we run trials, we run tests. So this is tangent of 360 divided by 2n, which in this case was 36, but still, like if we're trying to formalize something, right? So this is the generic what could work for all polygons if we know the edge length. So then it's altitude, so I'm going to go ahead and say A over, well, in this case it's going to be 7.5, but if we're trying to like formalize it, I'm going to scooch more of this over now because I think we've seen the shape enough. What if I'm trying to make, so if I'm trying to build something that might work for all shapes where we know the edge length, then this is going to be tangent of 360 over 2n equals, what would I build in this fraction for something that is always going to work? Well, wait, opposite over adjacent. Crap. I think I got this upside down. Because if I'm using 36, I was waiting for somebody to catch me on that, right?
Okay. Wait.
7.5 over A.
See, I wanted to do 54. then no one else did that. So then
Yeah, but this central angle is a little bit easier to find. Like, I know it's just one more step to get to the 54, but if I can do this, I mean, I guess you could have plugged in 180 minus 360 over 2n. But, so altitude, I'm going to go ahead and label this altitude. What would this be? How did we get the 7.5?
dividing it by 15 by 2.
So edge length divided by 2, right?
Yeah.
So the edge length
Isn't that another number though?
well, okay, E is a mathematical number, you're right. But if we're talking edge length, I mean, we should L. I don't know what you want to say. Do you want to say L?
I'll say EL.
Jake, you got to make sure that we're not saying anything we're not allowed to say.
I'm trying to think.
A lot of times we use cursive L for edge length.
X, so then you switch it. No, you don't.
Yeah, you do. These can swap places.
I was right.
Yep, because the proportional relationship.
Yeah. So then X.
Did you get like 10?
I'm not finished. I'm writing it down first.
It's not like I told you the exact answer.
I'm just. 10.32. So then that times 5. No, that's not right. So that's 10.32. Do 10 times 0.3, 10.32 times 7.5. Okay, add me back. That's 77.42. So that times 5.
I'm not. That 5 is not where it should be. A little under 400.
387.11 units squared.
So, challenge. Can we write this using generalizations? No specifics to the shape. So we just said the altitude could be found this way, right? So if I rewrite this, it is that the altitude, Jake, this is where we're going to try to formalize it and do what you were trying to do. So see if it makes sense. Because I don't know if it makes sense or not, and it may end up too complicated to matter. But the altitude is going to be the edge length divided by 2. L divided by 2. Divided by the tangent of 360 divided by 2n. So that's our altitude, right? So actually, I'm going to write altitude beneath it. What did we then do with the altitude? What did we do with the altitude over here?
Multiplied it together.
What was this 7.5? Yeah, it was that L divided by 2, right? So this all times L divided by 2 Then what did we do? We did times 5 then.
So, number of sides.
So times n now.
And then you do it. That's the area.
So this is our cleaned up area formula. I feel like there's a way that we could clean this up a bit more. Altitude times base, right? We could call that base times number of sides. Huh. I'm feeling like we'd have to be very, very, very careful. We did. Well, you want to check that it works with other shapes to make sure that it doesn't fall apart.
Yeah.
So it works at least here. So you have a conjecture, right? So you've gotten it to work. To make it a theorem, you have to make sure it can't fail. Are we still like, because theorems are agreed to be true. A conjecture is what we believe works because we've seen it work. But we need to continue to test it and make sure it doesn't fall apart. Was there more I was supposed to teach you today? Oh, by the way, the altitude is actually, because it's inside of a polygon from the center of the polygon, if you would like to write down this fancy word, the altitude is actually called the apothem. I forgot about that vocab word. So altitude, we actually call the apothem. Jake, what do we call the altitude? The apothem.
Why do we call it that?
Because it's coming from the center of a shape, perpendicular to the edge. Oh. Mr. Hall's asking.
I think it's 18. It's 20. Okay.
We were too slow.
So that's what I came up with.
Wait, this is what you came up with?
Yeah.
Yeah, because I was about to say, this has stuff filled in. So, n divided by 2 squared?
Yes. So what I got from it was altitude times tangent of 360 over 2n, then altitude equals n over 2 times 360 divided by tangent of 360 over 2n. So this times this is just n over 2. Because these cancel out. And then n over 2 times n over 2 is n over 2 squared.
I honestly, being honest with you, I can't verify this just by looking at it. Like, I'm not smart enough. Like, I'm not good enough at math. I shouldn't say smart enough. But, like, without me testing this and playing with it, I'm not sure if it works or not. It looks like it probably could. I'm just not sure. So, my advice, my serious advice, I'm not doing the teacher thing. My advice, try that, right? Test it. Do it with some things like I've got the answer key, right? So if you want to try it on something and then say, hey, is the area whatever, like, we can do that.
Is that all we have of all the rest of the chapter?
No, this is just the rest of chapter 8.
Ow.
All right, have a wonderful rest of your day. I guess since 7th grade is coming in, they're chasing us out. So, see you guys.
Get out. We're chasing you. Yeah, we're scared.
Hey, remember, math lunch is going to be serious.